Hello everyone, Nicola here. I've been working on a small side project that I'd like to share with you, with the hope that some of you may find it interesting. I've been reading a lot about evolution lately, so I wanted to create a simulation where I'll have some creatures that would evolve over time. I spent a lot of time thinking about different approaches and eventually came across something called NEUROEVOLUTION, which is a genetic algorithm for training neural networks. A particular implementation that we'll explore today is called NEAT, which stands for NEUROEVOLUTION of Augmenting Topologies. As usual, instead of doing the project that I wanted, I somehow ended up implementing the NEAT algorithm from scratch. That turned out to be way harder than I expected, but I've learned a lot, so I thought it would be fun to share some technical details with you. Before diving deep into the project, let's quickly remind ourselves what a neural network is. A neural network is a machine learning model inspired by how the human brain works. It consists of neurons which are connected through synapses. You can think of a neuron as a single number. This number tells us whether the neuron is active or not. 0 means the neuron is not active, while 1 means it is. We call this number an activation value. But how do we get this number? We can think of a neural network as a directed graph where neurons are represented as nodes and synapses as edges. Each edge has an associated weight that determines the strength of the connection between the two neurons. To compute activation value of a neuron, we compute the weighted sum of all of its input neurons and their corresponding weights. But the value of this number can be anything, and we'd like to have some kind of threshold to activate a neuron. This threshold is called an activation function, which we apply to the weighted sum to get the activation value. A well-known activation function is a sigmoid function, which is also known as logistic function, because it maps any value to a number between 0 and 1. For values greater than, say, 3, the sigmoid activation value is close to 1. In our example, the activation value is close to 0, so the neuron is not active. But what if we want to activate the neuron for smaller values? We can do this by associating a term called bias with each neuron and adding the bias to the weighted sum before applying the activation function. Bias essentially shifts the activation function to the left or to the right and allows us to manipulate the threshold. Neurons are typically divided into 3 groups: input, hidden, and output neurons. Values of input neurons are the raw values provided to the neural network. Hidden neurons are useful to learn intermediate patterns, while output neurons represent the final decision of the network. So, how do we choose weights, biases, and activation functions? This is done through a process called training. Neural networks are usually trained by giving it a lot of training data with correct answers and then course-correcting its decisions until it gets better. The most famous algorithm for training neural networks is called backpropagation. Another way of training neural networks is using reinforcement learning techniques, where an AI agent learns to make decisions by interacting with an environment. One such algorithm is the NEAT algorithm. Before we talk about NEAT, it's important to have a high-level understanding of how genetic algorithms work, so bear with me while I give you an overview. Genetic algorithms are optimization algorithms inspired by how evolution works in real life. They are used to find solutions to the problems by mimicking principles of survival of the fittest. The first step is to initialize a population. Each individual has a set of genes called the genome, or chromosome. Each genome represents a possible solution to the problem, but the solution doesn't necessarily have to be good, and we need a way to evaluate it. The evaluation is done using a function that takes a genome and gives us a number which describes how good the solution is. We call it the fitness function, and the evaluation number is called fitness. Genetic algorithms start by evaluating the fitness of each individual and selecting the best. The selected individuals are used to produce the next generation. For example, we can choose a pair of individuals and combine their genomes to produce an offspring similar to genetic recombination in biology. The idea is to mix the genetic material of 2 promising individuals with the hope of creating an even better one. This process is called crossover. Occasionally, random changes are introduced when doing a crossover of 2 individuals. These changes are called mutations in biology, and they add genetic diversity to the population. Mutations are the only way for species to evolve, so they are fundamental to our existence and is the same in computer science. The algorithm stops when it reaches the desired fitness or it can't find more improvements. We will distinguish between two important terms, genotypes and phenotypes. Genotypes are the actual genes. For example, I may have genes with traits for both blue and green eyes, and this would be my genotype. On the other hand, phenotypes are the visible traits. For instance, I have green eyes and this is my phenotype. But why is this relevant? Well, even though I have green eyes, I could still have children with blue eyes. It just happens that green-eyed genes are more dominant in my case. We want to maintain this property in computer science as well. In the NEAT algorithm, for example, a neural network is a phenotype, while the information for constructing the neural network is the genotype. This is useful if we want to disable some traits in a neural network, for example an edge, but still be able to pass it to offsprings. Okay, let's go back to the NEAT algorithm. We've said that NEAT is a genetic algorithm, so what would the genome look like? It's important to encode genomes in a way that enables a useful crossover. This means that we want to take two neural networks that are performing well and combine them in a way that preserves good properties most of the time. Let's look at two neural networks that have the same structure. We've said that each neuron has an activation function and a bias, while each synapse connects the two neurons and has a weight. To produce an offspring, we can select a subset of neurons and synapses from one network and choose the rest from another one. A second option is to combine individual properties of corresponding neurons or synapses. I decided to go with this approach. But how would this work if the two networks don't have the exact same structure? At least for the common part, we can do the same. The neurons and synapses that are not in both parents are called excess or disjoint. We will keep the disjoint genes from the fitter and ignore the ones from the less fit parent. But how do we find the matching neurons and synapses? The original paper introduces a notion of innovations, and I encourage you to read it. I'll try to explain this in my own way. A general idea is to assign a unique ID to each neuron. Two neurons are considered the same if their IDs match. Now that neurons have IDs, we can use them to identify synapses. Two synapses are the same if they connect the same neurons in the same direction. Let's write some code to represent genomes and implement the crossover. We will have two types of genes. A neuron gene that has an ID, bias, and activation function. And the synapse gene that I prefer to call a link gene, which has a link ID, weight, and whether it's enabled in the phenotype. Neurons and links are grouped into a genome or a chromosome, which has enough information to construct a neural network. To implement the crossover of neurons, we will choose the bias and activation from either parent at random. We use the same approach for the crossover of links. And finally, let's implement crossover for the two individuals. In this project, the difference between the genome and the individual is that the individual has a fitness. Let's now create an offspring. The offspring inherits inputs and outputs because these never change. I'm calling the fitter individual dominant. Let's cross over the matching neurons or keep the dominant neuron if the recessive counterpart doesn't exist. We will repeat the process for the links and we have an offspring. Now let's talk about mutations. In biology, mutations can happen in various parts of the DNA sequence during the crossover or due to external factors such as radiation. I'll split the mutations into structural and non-structural. Structural mutations add new genes to the genome, while non-structural mutations mutate the existing traits of a single gene. I'm going to implement 4 structural mutations in the NEAT algorithm. First one adds a link between two neurons. This is implemented by choosing a random input or a hidden neuron and a random output or a hidden neuron, and adding a link between them if possible. If the same link already exists or the link introduces a cycle, the mutation terminates. The next one removes a link between two neurons. This is done in a similar way as adding a link, but we don't have to worry about checking for cycles. The third one adds a hidden neuron. This is implemented by choosing a random link, then splitting it by adding a new neuron and two new links. The old link is still kept in the genome, but is disabled so it doesn't show in the phenotype. The weight of the first link is set to 1, while the weight of the second link is the same as the weight of the old link. The idea is that the new individual will behave in the same way despite having a different structure. This is because the combination of the two new edges should behave in the same way as the old edge. This is important to ensure mutations are not too drastic such that new individuals don't get a chance to prove themselves. And finally, the last mutation removes a hidden neuron. This is done by removing the neuron and all the links that connect to it. Non-structural mutations are simpler. They mutate an existing neuron or a link by mutating each of the individual properties with some probability. The most common mutation is to update numbers. Each number has a config that specifies how disrupting the mutations are. Initial values are chosen using normal distribution. A mutation occurs with a given probability, and if it occurs, the current value changes by adding a random delta to it. The delta is generated using normal distribution around 0 and a standard deviation that we call the power in the config. There is also some chance that the number will be fully replaced by a new initial number. Also, each value is capped to avoid overfitting. Okay, we have implemented the crossover and mutations. Let's create an initial population, run it for a number of generations, and save the best individual. I'm using protobufs to serialize genomes that some other program can load later. For the initial population, I will create genomes that contain only inputs and outputs because the mutations can add new hidden neurons. One of the advantages of using the NEAT algorithm is that it can find the optimal structure for the neural network. Input neurons don't have an activation function or a bias, so we don't need to store any information in the genome except for the number of inputs. On the other hand, outputs are the same as any other neuron, so let's add them. The genome also has to store the links. There are a couple of strategies regarding the initial links, but I decided to generate a fully connected feed-forward genome, which means that there is a link with a random weight for each input-output pair. We will use negative numbers to represent input neurons as a convention. I've seen this implementation detail in the Python NEAT library, which makes it easy to debug the network later. With the initial population ready, let's compute the fitness for each individual and update the best one. We should really be running this for a number of generations and replace the population with offsprings, so let's do that too. We'll come back to the fitness function later. Let's first implement the function that produces offsprings. We want to select the best individuals, so we sort them and compute the cutoff. Then we produce the number of offsprings by choosing two parents at random, combining their genes, and mutating the offspring. And now the next generation is ready. We haven't talked about creating neural networks yet, which we need before we can implement the fitness function. Let's see how to do that. We want to compute the activation value for each neuron, and to do that we need to know all the inputs for the neuron, including the bias and the activation function. Let's store this information into a struct called neuron. We are organizing data such that it's easy to find the relevant information for every neuron. To implement the neural network, we need access to neurons as well as input and output IDs. We could technically just keep the number of inputs and outputs and then use the convention we just talked about to construct the IDs, but I don't want the neural network to depend on those details. Let's implement the activation function first. We will compute activations for neurons and store them in the values hash map. Inputs are stored without any changes, and the order of input parameters matches the order of input IDs in the neural network. All outputs are initialized to 0 because the network must return a value for each output, even if it doesn't have any links. Now we can iterate over each neuron and compute its activation value by taking the weighted sum of all input activations and their corresponding weights. Then add the bias and apply the activation function. Finally, let's return the computed activations for each output. All that's left is to construct the neural network from the genome. Some of you may have realized that the order in which activations are computed is important. We can only compute activations for neurons whose all inputs are already computed. We will solve this problem by creating layers of neurons. Neurons in a layer are activated after the neurons in the previous layers. To make our life easier, let's remove the neurons that are not required. These are the neurons that don't have any inputs connected to them, so they can't affect outputs either. The first layer of neurons are inputs and we mark them as activated. The following layers are constructed by selecting neurons that can be reached from the previous layer, assuming all of its inputs are activated. The process repeats until all reachable neurons are activated. Once we have the layers, it's easy to construct neurons. Okay, that was a lot of work. Unfortunately, the neat algorithm on its own can't do much. We need a concrete task that can be evaluated before we can train the AI. I really want to test this on a simple 2D game, so let's write a game engine for an old snake game. The engine takes an action and returns a game result. The snake can keep going in the same direction or rotate either left or right. We will store the snake body as a deck of 2D coordinates with a head at the front. To update the position of the snake body, we find the next head position and check if it hits the wall or itself. We should also remove the tail. I want to allow the snake to make a full loop, so let's remove the tail before checking for collisions. We also need to check if the snake has just eaten the food, and if so, spawn the food again and increase the size of the snake. I couldn't think of a smart solution to generate food without adding too much unnecessary complexity, so I decided to implement a naive solution that generates food at random until the chosen slot is free, and this seems to work fine for now. We should probably test the engine before using it for training neural networks, but that seems too boring for a project like this one, so I decided to create a simple UI and test it by playing the game itself. I have never used the SFML library in C++ before, so I thought this is a good opportunity for me to try it. I'll need some kind of UI to watch the AI play the game anyway, so it makes sense to do it now. Let's start by creating an empty window. I'm going to separate the game rendering logic in the game renderer class, which will have access to the SFML window and the engine. Let's initialize the engine and draw the grid for the game. Unfortunately, I don't think it's possible to draw only a stroke of the rectangle in SFML, so I'm going to work around this by filling the background in the color of the stroke, then draw the grid fields in the actual background color. Let's also integrate the game renderer with our main logic, and we have the grid. Now it's time to draw the snake. And let's also add the food. This snake is a bit boring, so let's make it alive. I want to control the snake with arrow keys, but also have an AI control it later. So let's add the controller interface for this. For example, detect if an arrow key has been pressed, and we can get the desired action using the getAction method later. The reason I'm splitting this is to capture keyboard events on each window frame, while the game state updates are controlled with the frames per second config. Let's go back to our main loop and integrate the controller. I'll also add the ticker that controls the frame rate of the game. I forgot how much fun this game is, but the colors don't feel quite right. I want the body of the snake to change color with each segment. Unfortunately, SFML doesn't have support for HSV colors, so let's quickly add RGB to HSV conversion and vice versa. Now we can use different luminance, maybe the snake will get darker towards the tail. We can choose the luminance from the segment index. That looks much nicer, but it still doesn't feel quite right. Let's try different colors. It starts off a bit weird with just a few colors, but I really like how we see more colors as the snake grows, so I'll stick with this for now. I've also added a score and handling for game over, but that's not interesting, so I'll spare you the details. The game seems to work now. This is not really a comprehensive testing, but I feel like it's good enough for this purpose. Let's now implement the fitness function. We create a game engine with a random state and build a neural network from the individual's genome, and then run the action produced by the AI until it's a game over or it's been running for a while. I'm limiting the number of steps to avoid infinite loops. But how does the AI controller work? To use the neural network, we need to extract the relevant information from the game engine, feed that information as inputs, and the neural network will return activations for each output neuron. We can then choose the output with the highest activation value, convert it to the corresponding action, and process it. So, how to extract the inputs? There are many ways to do this, but I'll start with something very simple because this was a lot of work and I want to see it in action as soon as possible. For now, let's create 4 Boolean inputs. These inputs represent the snake's eyesight in 4 directions. I'm going to encode the vision with 0 or 1 depending on whether the food is present. The values are ordered relative to the snake's direction. It's time to train our AI. Let's train it for 100 generations. It seems like it's making some progress. The winner has collected food 11 times on a 40 by 40 board. It must have been very lucky since its inputs are limited. Its strategy is to turn towards the food as soon as it sees it, but it eventually hits the wall and dies. This usually happens very quickly. Let's have a look at how the snake brain looks like. It's very simple, but let's add some more information. For example, we can add information about the wall. I'm going to add the distance to the wall in the same 4 directions, and normalize it such that 0 means the wall is very close, while 1 means the wall is very far. Let's train it for 100 generations again. The training is now taking some time because the snake is actually doing something reasonable. The best individual reached a score of 110. Let's see how it's playing. It seems to be doing quite well. Let's speed it up. The snake is very careful. It only goes towards the food if it's on the left side. It also seems to prefer going all the way to the walls instead of turning towards the food immediately, but this is not very consistent. I wonder why. I don't quite understand the strategy, but it's not bad so far. And it eventually gets stuck in the loop. That's unfortunate and seems to happen only when the food is in the middle. Maybe it needs more training. Let's try for 500 generations. It's doing a bit better now. It doesn't seem like it gets stuck in the loop, but it ends up eating itself. Let's add the vision for the snake body as well. We'll add inputs that detect the presence of the body in each of the 4 directions, similar to what we did with the food, but also the distance like we did for the wall. In total, we are adding 8 new inputs, 2 for each direction. Let's train it for 500 generations again. It's doing quite well so far. I'm so happy to see it avoid its body. Why did it turn towards the wall? This makes no sense. Looking at the debug logs, it wanted to go both forward and turn left with roughly the same probability. The networks are getting a bit more complex, but not by much. It's possible that mutations don't survive for a long time because it's unlikely that they would improve fitness immediately. We need to keep the mutated individuals around for some time to give them a chance to evolve. For example, if a mutation introduces a new edge, this may reduce the fitness, even though the new structure may have better potential fitness. Neat solves this problem by grouping individuals into species that have similar genomes and allowing reproduction between individuals only if they are in the same species. The distance between 2 genomes is determined by counting how many genes are different, which is easy because we can simply compare their IDs. Also, it considers the difference between the same genes, such as how different the weight or bias is. After the reproduction, each individual is assigned to any species whose genomic distance is within the threshold. If no such species exists, we create a new one. This will hopefully help with the training because it's getting stuck at the local maximum at the moment. We'll also keep the track of when was the last time the species improved and remove the ones that were stagnant for a long time. This will create space for new species. Let's try training the AI again. The speciation helped a bit, but it didn't improve fitness much. I have experimented with a lot of different approaches and even tried to train the snake in Python with the Python neat library, but I didn't get better results. I've tried changing activation functions, training for longer, using single output neuron, reducing the noise by running the game multiple times and taking the average score, but nothing helped. The snake has enough information to do better than it currently does, but I failed to achieve that with the neat algorithm. If anyone has any suggestions for improving it further, please let me know in the comments. Even if it can't be improved, I appreciate that doing lots of random things can produce some reasonable solutions. By the way, if you're enjoying this video, please hit the like button and don't forget to subscribe. Also, consider sharing it with your friends, it would help a lot. For my final attempt, I want to prove that the agent has enough information to perform better, so I decided to create my own genetically modified snake. I've carefully handcrafted the weights, biases, and a few hidden neurons, and I got a snake that consistently performs better than the one produced by neat algorithm, even though it only reads a few inputs. The snake gets a positive signal if there is food on its right or the wall is exactly in front of it, and a negative signal for going forward if it's about to hit the wall or itself. Also, it gets a negative signal for turning right if it will hit the wall or itself. What's interesting about this is that the AI might sometimes turn left if both forward and right turn actions have high negative signals. So in this model, I didn't explicitly tell it to turn left ever. Let's see how it performs. Nice, it reached 155. That's quite good for a very simple network. I was also going to try the official benchmark with a double pole balancing task, or maybe build a Flappy Bird clone, but this video is already too long, so I will leave that for another time. I hope you've enjoyed this episode of Coding Quests. I may occasionally upload videos like this, so let me know if you'd like to see more such videos. Also, you can now support me on Patreon. See you in the next one.